Oxides. Oxide chemistry, very important type of ether. Oxides have lots of application. Epoxy glues. We looked at synthesis of epoxides last time. We're looking at reactions with like HX under acidic conditions. I think we did the first one in class. Is that right? Did we do this one? Dominique, did we do that one? Yes.
We did both those.
We did both those in class? Did we do this one in class? No. Okay, we got HCl. What's the first thing we're going to do? Protonate that. We got Cl minus. That's the nucleophile, right? Any other possible nucleophile around? No. Possibly. I mean, this is aqueous. Although it doesn't have to be. HCl can be dry. I mean, it's kind of up in the air. It could be water. Usually for me, if it's going to be water, I'll put an aqueous or H2O. Or we'll use sulfuric acid. Because if you want to use water as a nucleophile, you don't want to have Cl minus around. Okay? We don't want to have competing nucleophiles. Here's our nucleophile. What type of mechanism we're going to do so we can predict a product? We can either end up attacking here, or we can end up attacking there. Which one do you want to do, top or bottom? Bottom, by what type of mechanism? SN1. That means we're going to ionize this off. The oxygen just leaves. If the oxygen leaves, what do we get? Carbocation. Here it is. It's both forward. Okay, that oxygen's forward. This just breaks away. But it's still forward. That bond, nothing happened here. This is still forward. And this was an OH. That was the leaving group, right? That just left this carbon. I'm going to draw that a little bit more precise. What's on this carbon? Methyl. Is it bold, dashed, or what? It's actually in the plane because this is a carbocation and that's trigonal planar, right? Here we got something new to consider. Maybe my guys, we mentioned this in Organic 1, but epoxides, ultimately what's going to happen next? Cl minus attacks here. We would show product. And what type of stereochemistry would we expect here? We might expect racemic. And so that would be that. This we would show just a Cl. That's connected, right? That's my bond. And we would say racemic. There's also a melt one. Good. That's a chiral carbon, but we're saying it's racemic. Racemic because the chlorine can attack from the front or the back. 50-50 chance. That's a planar sp2 carbocation. And you might say that's the product. Up here we maintain our stereochemistry because nothing happened up there. The leaving group just is forward. It just opens up, but it's still forward. Okay. Actually with epoxides, this is not the outcome for the stereochemistry. With epoxides, SN1 with epoxides gives inversion. Now why? Because when this leaving group leaves, is it really gone and way away? No. What happens is, even though this left, there's significant amount of sort of association between the lone pair and the carbocation. It doesn't totally leave. Because it can't swim away way over there, It's stuck there. There remains some association between the electrons, which are minus, and the plus. Everybody agree there'd be some association there? There's enough association there to block that side. Now this is up. The association is coming from here, so it's also up. So it's sort of blocking the upside. So the chlorine actually comes in, how? Backside, which for us here is bottom. So it sort of comes in and it breaks that association. But now you might say, well, this looks like an SN2, where this comes in and kicks off the leaving group, right? That's because what it really is sort of a blend. But the first thing is it's SN1. Here's how we're going to do. It's an SN1 that happens to also have inversion because the leaving group still associates a little bit. We're still going to say a cation. And if you got a little bit more precise about it, this association causes this to only be a partial plus, and that becomes partial plus. That would be more definitively or more accurate. But I'm just going to keep the cation there and say because of this sort of back bonding, that's what we call an organic 1, it blocks the high side. Okay? This thing is here, it sort of back bonds a little bit. There's some association here. When that chlorine comes in, it's like, okay, I'm going to come in the other way. So you actually get inversion there. And so the product is what? This is bold. This down here is going to be what? Draw that in down there. Is the chlorine going to be dashed or bold? Yeah, it's going to be dashed. And the methyl is going to be thus what? Bold. Because the methyl, which is down, I'm calling it down, it's really back. Okay, the oxygen's forward, the methyl's back. But the chlorine comes in from the back, and as it comes in, it kicks that oxygen completely off. What does it do to the methyl? Pushes it forward. That's the inversion. And so, what we got here is an SN1 with inversion. That's unique to epoxide. It's unique to other things too. You actually get it with bromonium ions. But back when we covered bromonium ions in organic 1 for me, we didn't even know what SN2 or SN1 was. So, SN1 with inversion, can we go with that? Are we willing to go with that? The epoxide. Now how do we know that it's SN1 with inversion? Go run the reaction. That's what you're going to get. We're not making this stuff up. It's analogous to that there. If chlorine came in, like if you're acting with BrCl, you would come in here, we'd kick this off, and we would get, this would be bold, this chlorine would be dashed, methyl would be bold, and this is if we reacted alkene with like BrCl, mixed halogen. This could be another Br. If we reacted this alkene with Br2, it could be another Br. And doesn't bromine add trans? Yeah. What mechanism did it just do here? Somebody? Well, it's kind of mixed. I mean, nucleophile and leaving group off, what's that? That's SN2. But hold on, if we were doing SN2, I should be attacking up there, because that's the least substituted site. Why are we attacking down here? Because it's really a cation that has some significant back bonding. But again, when we covered this in organic 1, we didn't even know what SN1 or SN2 was. If you're going to do SN2, you should tack here, right? It's the same thing. I mean, I could show this ionized off, show the cation, and back bonding makes it trans. If there's no back bonding, you should get racemic. Okay, other nucleophiles. Acid, other nucleophile. When you're using acid, your nucleophile cannot be strong. Acid and strong nucleophiles are not compatible. Just like hot water and cold water are not compatible. You can't have both. If you fill up your tub with a mixture of hot water and cold water, what you going to get? They're going to neutralize each other. You're going to get warm water. You can't reach in there and say, I want the hot water, and then now I want the cold water. No, they're going to mix and neutralize. Acids and bases will neutralize. Strong nucleophiles are bases. Okay, we've got H plus. Aqueous, what's the nucleophile here? Water. Sulfate is never going to be a nucleophile for me, for us. The only thing here is water. That's going to be the nucleophile. Protonate the epoxide. What you want to do now? You want to take the left or right? What's our rule that we're going by? Somebody said left. Why left? Do we have a tertiary side available? Then we're going to go SN2. We're going to go SN2. Which one are you going to attack? The least substituted. Water then comes in, attacks here, kicks the leaving group off. What do you get? Boom, boom, boom. The leaving group just opens up. This is still bold here. There's a leaving group. It's now a neutral OH. What's now on this carbon? Water is now bonded to that carbon. Mechanistically, do not lose any H's. We haven't lost any H's yet. And that oxygen is plus. Now we have to take care of a proton. We'll have to do that in lots of cases. We want to remove the proton, go neutral. What can remove it? HSO4 can do it. You could also use water. So there's going to be excess water. I typically use H2SO4 and I don't draw a Lewis structure, so I don't draw a lone pair. It's okay to just do this. This takes the H, these electrons stay behind. What do we get? We just get our product, which is OH. OH plus what? H2SO4 reformed. The reactants here are really water and H plus catalyst. That's what we got here. We used the water, the sulfuric acid was just the catalyst. We used the proton, but the proton then went back to where it came from. Acid catalyzed addition of water to the epoxide. By what type of mechanism did we do here? That's a good old SN2. We're not even considering a carbocation. Because if you consider the carbocation, you'd form it over there. Right? Good old SN2. What type of product did we make? What do you want to call this? Alkane? What do you want to call it? Alcohol? What do you want to call it? It's actually a diol. Yeah. Opening up an epoxide with water gives a diol. We made diols in Organic 1. No, we didn't. Some of y'all might have did. Dr. Adele might have covered reactions in Organic 1. We've seen a diol here earlier. What was it in? THC is made from a diol, right? I showed that. Okay. Show the product in the next reaction. Sulfuric acid, yes, it's aqueous. I got this methanol in there. That's going to be your nucleophile. sulfuric acid is just going to be your catalyst. Yes, there is water here, but see the alcohol, use the alcohol as your nucleophile. Show the product there. And then show the product for the reaction below that too. Down here. So to predict the product, we use our mechanistic knowledge to predict products. We're under acidic conditions, so we're going to protonate something. The oxygen is only protonate. Methanol is our nucleophile. What are we going to do here? Hey, this is, did y'all realize this? I mean, you can either do SN1 or SN2. We know SN2 gives inversion, always. SN1 gives inversion with epoxides, so that means everything you do is going to give inversion. Now I would hope that as studying, you all realize that and find consistencies, and then boom, makes your life a whole lot easier. There's a lot of things like that you can say, hey, I can't tell you every single one or I'll forget them. That's you being an active studier and trying to organize the material and look for consistencies. Yeah, everything gives inversion with epoxide. Now what if you see a product and you're asked to give a mechanism but the product does not have inversion? What if it's racemic? What does that mean? It means it must have been a cation without significant backbinding. So a predicted product is one thing, a mechanism where something's shown and you're given information with the product. Okay, down here, methanol. You want to take top or bottom? It don't matter, they're the same. This is a symmetrical epoxide, right? Either way, everybody see this is symmetrical? It does not matter. I'm going to attack the bottom, does not matter, you get the same product at the top. Are we doing SN1 or SN2? Actually, it doesn't matter, we're just going to kick this off. I'm going to do a pure SN2 because that's secondary. What does that give? I'm going to give, the group just gets kicked off, no change there. It's forward, just gets kicked off, but it's still forward. Down here, we have now bonded to this is the methanol. Is it going to be forward or back? It's going to be back. That's oxygen with a methyl and an H. One lone pair. The other lone pair bonded here. That's a plus charge. What do you want to do now? We just want to go neutral and we get our product. Take the H, lone pair stays behind. We get that product. It's not a diol because water didn't react, methanol reacted. So this is OME after we lose the H. Make sense?
Question. Would there be an enantiomer for that? Or an enantiomer? Because if you attack from the other side, then it would be a mirror image and you can't superimpose it. You attack from the other side of the epoxide.
You mean if you attacked up here?
Yeah.
let me draw the product. What would you get? You would get the leaving group would leave down here. This would be backside here.
Are they, mirror images?
Okay, you're exactly right. Good. That would be an enantiomer. Yeah. This and that are enantiomers. I was thinking this was chiral, and my first thought is there should not be an enantiomer. It's a starting with chiral, but this is actually not chiral. That's the problem. This is not chiral. There's a plane of symmetry. It's not optically active, and so your product can't be optically active. If we react this and only get this enantiomer, this is chiral. There's no plane of symmetry. It would be optically active. We'd have a Nobel Prize. But you also get 50% of this, and the mixture is not optically active. 50% of this causes 50% chance of attacking here and 50% chance of attacking there. Very good. I would just accept that product there for predicted product, unless we talked about stereochemistry and we want to get more involved. Yeah, good point. That's the enantiomer over there. Because if we flipped it to make the OME down, the OME would then be bolded. See there, it's back. If we made the OME down, it would be forward. Okay, what's the product, the next reaction? What's the nucleophile? Acetylide anion? What do you want to do first? Protonate something? Got an acid, what do you want to protonate? H plus. Now the first thing that's going to happen is this going to protonate, and you're going to get that, and then you have no nucleophile, game over. No reaction. You cannot have a strong nucleophile in the presence of acid. Which is more basic, a neutral oxygen or a carbanion? Hopefully you rationalize that a carbanion is more basic. You cannot tell this reaction, okay, carbanion, I only want this to react. You just have to sit there and not react with protons. No. Acid-base reactions are instantaneous pretty much. No. No reaction. You cannot have a strong anion in the presence of acid. You can have methanol in acid. You can have water in acid. You can have Br minus in acid because HBr goes to that. I mean, that's how HBr exists. You cannot have a carbanion in the presence of acid. That would have to be under basic conditions. Takes us here. Under basic conditions, hold on, I thought ethers were unreactive under basic conditions. We said that earlier on the other page. Standard ethers are unreactive under basic conditions, but epoxides are reactive because of the ring strength. Let's look at that. Under basic conditions, we're not going to protonate anything. Strong nucleophiles. First off, under basic conditions, guess what? Always and only SN2. Okay? Never SN1. Strong nucleophile, it's going to be bimolecular, it's going to be SN2. Since it's SN2, which carbon are we going to attack of the two? Most substitute or least? There you go. Always. What we're going to do here is mainly look at types of strong nucleophiles. And the first one is what we just looked at up there. Acetylide anions. Called an acetylide anion. Alkyne carbanion, more generally. How do you make those? If you remember terminal acetylenes or alkynes, the H is somewhat acidic. Has a pKa of about what? 25. List of pKa's is in the last sheet of the workbook. A couple of different bases that are used to this. Sodium amide, sodamide, Na plus, NH2 minus. These electrons take the H, these electrons stay behind, you get lone pair behind, and you make ammonia. This is a lousy base in practice, but textbooks love to use it. No chemists love to use it, just textbooks. It won't dissolve in anything hardly. And if you dissolve it in water, then you just got hydroxide. Okay, but we do this. How do you judge an acid-base equilibrium? You got to know the pKa's for both sides. What's the pK of ammonia? Good, it's about 30. Which side's favored, 25 or 30? Weaker acid's favored. This side's favored by how much? Favored by 10 to the 5. What's that, 100,000? Yes. Still pretty much going to be a favored reaction. We can also make the product with N-butyl lithium. One carbanion forming another. Same mechanistic arrows, we would get this plus butane. Butane is greater than 40, not acidic at all. Which is favored, 25 or 40? 40. By 10 to the 15, that's 100 gazillion. N-butyl lithium. See here, we're going from an sp3 carbanion to an sp carbanion. It's a more stable carbanion, that's why the equilibrium is favored, even though they're both carbanions. Right? Remember hybridization? That's why this is stable. That's why that's acidic enough. Once we make it, then we can throw in an epoxide. This is the simplest of epoxides, just 2 carbons. This would attack here, kick the oxygen off. Either carbon, you get the same thing. SN2. This electron movement would give, should have attacked over here. You attack, there's your 2 carbons, here. Okay, this is a neutral oxygen leaving. Can a neutral oxygen be a leaving group? Not usually. Never usually. If you make it a tosylate, it will leave as a neutral oxygen. Why is it able to leave here? Ring strain of the 3-membered ring. You open that ring up, and the molecule goes, ah. The oxygen of an epoxide will leave if you've got a strong nucleophile. When it leaves, what does it become? It becomes O minus, right? 2 lone pairs, 3rd lone pair now. Now at this point, to go neutral, we have to supply a proton. That's either going to come from an acid or water. Either one will supply a proton, we can go neutral. One thing we'll say about this is, I'll go ahead and say it now, that was our nucleophile. Any epoxide reactions, the ones we've already done, give nucleophile, carbon, carbon, OH. All right, we're back in 2nd grade. Y'all repeat this with me. Nucleophile, carbon, carbon, OH. If you look back at the top products, you're going to see nucleophile, carbon, carbon, OH. That's what you get from epoxide reactions. So, acetylide anions are one type of strong nucleophile that can be used anywhere, and we're illustrating with the epoxides. Another type, instead of acetylide, how about alkyl anions? We're eventually going to call these Grignards or alkyl lithiums. These are the most common. I mean, N-butyl lithium is an example of an alkyl anion. how do you make things like Untitled Lithium? If you have an alkane, like butane, you might say, well, let's remove an H and make the anion. It's actually very difficult with alkanes because they're just not acidic at all. Much easier with alkynes. And so this is usually not done. That light just go on? Instead, there's a couple of tricky ways to do this, to form your instead. Instead of starting with the alkane, we start with an alkyl halide. So maybe, for example, and I think these are shown examples on the next page. I'll do a little bit here. 1, 2, 4 carbon, maybe a bromine. So that's what this is, alkyl with a halide. It can be any halogen, usually not fluorine. The R group can be sp3 or 2. If you react such with a metal, usually it's a group 1 metal or group 2 metal. We'll see examples. The metal will actually insert, well, it'll be 2 different ways. You can get R metal plus MX, or you can get this. Let's go ahead and look on the next page, because it shows precise examples. You take, and this is a 3 carbon instead of 4. You take this, react it with lithium, which is a group 1 metal. It requires 2 equivalents. You can get the R metal, which is shown on the previous page, plus also metal X. Is that what was shown on the previous page? I think so. And that an R metal, and then that's MX, metal X. This is sort of redox chemistry. The more common one for introductory organic is with magnesium. Now that's a group 2 metal. And with group 2 metals, the metal just inserts between the carbon and the halide. And this is known when you use magnesium as a Grignard reagent. This is making the Grignard. Magnesium metal sometimes shows 0 because it's oxidation state of 0 metal. Diethyl ether or THF, these are ether solvents, very common for making Grignards. Now let's look at this. This is shown sort of covalently and just kind of formula. If we turn this into ionic, we know the Br would be minus. And actually, Mg is now ionic. What's going to be the charge of Mg? 2 plus. And then we got here, what's going to be the charge of this? This is going to be minus. And to be minus, it has a lone pair. If we showed this fully ionic, you would have your carbanion, which that's what we're trying to make. You'd have Br minus and Mg2 plus. But usually it's just shown like this. But consider it this. Now, here the magnesium is 0. Now it's 2 plus. Has the magnesium been oxidized or reduced? The magnesium has been oxidized. This is called an oxidative addition. We say the magnesium has oxidatively added between the carbon and the bromine. How does it do this? It's probably a radical reaction. It's probably redox radical. We're not going to show arrows for how it does it. But guess what? Victor Grignard back in like 1898 added some magnesium to such and saw a reaction. And then he was able to do chemistry and get essentially carbanions from an alkyl halide. Not by removing an H, but by essentially removing a halide. Okay? The lithium is up there. You require two equivalents because it has to be, it's not divalent. Questions about making these? These are called organometallics because they're organo and metal. Organometallics. Organometallic chemistry is a huge field of organic chemistry. Okay. Once you make these, they react as if they're carbanions. So let's do some reactions. We got this alkyl halide lithium to a foot. What's that going to do to this? We're going to make the alkyl lithium. That's what we did right up top. Now, I'm showing this covalent. It's actually in between covalent and ionic. It's actually usually a trimer or a tetramer. But we can consider this as that plus lithium plus. That's what was just stated up top, right above. And there's our good nucleophile. Now if we throw in an epoxide, what type of chemistry can we predict? Epoxides love to have nucleophiles come in and open them up. Do we have a nucleophile? Yes. These electrons come in. Okay, now we have, it sits here and it has to ask itself, which one am I going to attack? Left or right? Right. Right. It's always SN2. Kick that oxygen off. Can it leave? Yeah, with epoxides it can't. What does that give? I have that. I have a gold. What's now bonded to this carbon? Don't draw this, but isn't the nucleophile now bonded to that carbon? What is the nucleophile? It's a 3-carbon fragment. So we got 1 carbon, 2 carbon, 3. And we just made that bond. Because it's all carbons, I often see students lose track of how many carbons you got here. There's the original 2 of the epoxide. That was the nucleophile that came in. Used to be an oxygen, it left and just came here. The oxygen's this is in the plane. In the plane of the board, it just gets picked up, still in the plane of the board, and this is now what? O minus. Let's kick that off, it becomes O minus. And then you'll see something like this, appropriate workup. That is to put the proton on, such as adding in water or H+. Either one will supply the proton, and you get your final product. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. There you go. What was the nucleophile? Here. What do you get? Nucleophile, carbon, carbon, OH. Isn't that what we said we'd get? Take 30 seconds and do this one here. What does magnesium do to an alkyl or aryl halide? Converts it to the Grignard reagent. Magnesium inserts between the R group and the halide. And the R group is essentially then a carbanion. So the first step is to give the Grignard. THF is just a common solvent. This is essentially what? Essentially that minus I minus Mg2 plus. Now we've got a good nucleophile. Yes, it's on an sp2 carbon. We throw in this. Nucleophile can add left or right. These electrons attack here, the least substituted site. Kick off the oxygen leaving group. What do we get? We get the oxygen is straight up. So if it's in the plane, that bond here over here does not change. We have a bold methyl, and we have a dashed ethyl. Is the benzene ring of the phenyl group going to be forward or back here? Neither. Phenyl group is straight down. That's the benzene. I'm just going to call it pH, phenyl. I could draw the ring out. Straight down, right? So everybody agree that the nucleophile comes in the exact opposite of the leaving group? Backside? The leaving group is straight up, right? So how does the nucleophile come in? Straight down. I mean, here it is. That oxygen is straight up. It's not forward or back, is it? So the benzene ring comes straight down and kicks it off, all on the plane of the board. Not forward, not back. Here. Well, the methyl is forward, a little bit down. Here comes the nucleophile. Boom, straight up. Kicks the oxygen off. What happens to the methyl? It's forward. What does it do? Does it go back? No, this moves up to make room for this. It's still forward though. The methyl just moves up. With appropriate workup, that's how you get the H there. I'm not going to every time do a minus and then put the H on. Appropriate workup puts the H there. There's your product. Did we get it right? Questions? Just go to all SN2 backside. Amines. Amines are good nucleophiles in the neutral state. Good nucleophile. You don't have to deprotonate it. Strong nucleophile. So the mechanism is going to be what? SN2. I don't see a proton, so we're not going to protonate and do SN1 potentially. He's going to attack the top or bottom? Bottom. You are going to have to take care of the proton. Try these on your own. We'll look at them next time. Let's look at multi-step synthesis. We're going to do more multi-step synthesis. This is an intro, more of an intro. Look at this compound, terbutaline. It's used to control premature labor in pregnant women. Maybe also pregnant horses, I don't know. But not pregnant men. Anybody know terbutaline? No? How would you want to make terbutaline? Could you make it from an epoxide reaction? What type of product does epoxide reactions give? Nucleophile, carbon OH? Do you see a potential nucleophile, carbon-carbon OH, that you could break the nucleophile off? How about right here? Nucleophile, carbon-carbon OH? Not here, but what would the nucleophile be here? Actually be an amine. We didn't do an example, but it would be an amine. We could go backwards and we can envision that epoxide. I have to keep these over here. Reacting with what? A nucleophile, which would be NH2. Nucleophile epoxide. I envision making this bond nucleophile, carbon-carbon OH. Now, these electrons, that's a good nucleophile. It's going to do attack, would it attack left or right? Attack here, kick that off. That's going to give, I'm just going to call all that over there R. I'll give R. I'm not showing any stereochemistry here. It's going to become O minus carbon. What's now bound to this carbon? N, 2 H's, and the tert-butyl group. And we just made that bond that I highlighted over there. Now, that's a plus charge. Again, we did not do an example. This to go neutral, what has to happen? This has to lose an H+, and this has to gain an H+. This H+ can essentially move here. We will do this lots of times this semester. I'm just going to call this H+ transfer. And I'm not going to show a mechanism. I can show it briefly. There's millions of these molecules in the flask, actually gazillions. It's probably intermolecular. The O- of one molecule takes the H, leaves that behind, where this takes the, that's this part of this takes the H here. It's probably intermolecular. It's like all of y'all are that product. You need an H+, you need to get rid of one. So just take the H+ from her. You get the H, you lose one, that's what we need to do. It's probably intermolecular. We're just going to call it H+ transfer throughout the term, again, to save like an hour over the whole semester. In this case, we didn't have to supply an external H+. You know how we said appropriate workup? Here we have a built-in source of H+ from that original nucleophile. Okay, we'll see some of you this afternoon. The videos are going up. Quiz on Wednesday over everything up to now. From the beginning. Starting next Wednesday, the 2 new handouts. We'll be looking at oxidation of alcohols, also oxidation of alkenes. Next week in lab, we don't come back till Wednesday. We are doing the oxidation of the diol. Let me note that I'm probably going to turn that lab into an answer sheet instead of a report. It will probably be an answer sheet instead of a report. Next week's lab.
We still look at
You smarty pants back there. Just trying to be. I was like, yes! Dude, as soon as you said it,
Then are we doing
I was like, he's
lab?
absolutely right.
You don't get a tree. Okay.